And perhaps it's amusing to tell the story because I was reading at this time the beautiful book by Schrödinger about his life. And he spoke about entropy flow, entropy, how entropy enters into the maintenance of an organism. And then in the last chapter, I think, he comes to the problem how it happens that life is so stable, that after all, life has a well-defined organization which is transmitted from one generation to the next generation. And he said, oh, probably life must have a kind of stability like a good watch. Now, I found this explanation somewhat strange because a good watch has to be isolated. If you begin to hurt it, to bring it around in a too brutal way, it will stop to be a good watch. But life is not taking, life is not associated to isolated systems. So I thought that perhaps we have to extend the idea of stability to non-isolated systems. We know very well that an equilibrium system, an isolated system, is stable. It has a minimum free energy. When you change slightly the free energy, it will come back to the minimum. But what if the system is submitted to outside influences? And that was really the starting point of what became my theorem of minimum entropy production. And minimum entropy production means that when you have a system which is submitted to some flows of heat, for example, or flows of matter, and comes to a steady state, what characterizes in the steady state? It's no more the entropy, but it is the entropy production. And the entropy production is becoming minimum. And that means that the system is as lazy as it can be. It cannot come to equilibrium because you prevent it from boundary conditions, by boundary conditions, but it comes as near as it can to equilibrium. In equilibrium, it would have a zero dissipation. Now it has a minimum dissipation. But there was something interesting in this theorem, and that was the idea that the arrow of time, that the flows of heat or of matter to which the system is submitted, may have a constructive role. May have a constructive role indeed, because the minimum of entropy production is not the greatest disorder. On the contrary, for example, if you take a system which has two components, hydrogen and nitrogen, then in the steady state there will be, let's say, more nitrogen left and more hydrogen right. So it will have some organization. So irreversibility, the arrow of time, leads to a kind of more, I would say, a refined state, a state which you could not produce spontaneously at equilibrium. And that impressed me very much. And I became very interested in the constructive role of time. And time really is, I would say, historically a very important problem. Because in a sense, Western civilizations since Newton has always been in front of a paradox. Because, as you know, the laws of nature, which is the way in which we describe nature, the basic description of nature, is time reversible and deterministic. If you take Newton's law, once you know the initial conditions, you can predict with certitude what the system will do in the future or what it has done in the past. So it is deterministic. In addition, there is no difference between future and past. And curiously, in spite of the two great revolutions which we have known in the 20th century, quantum theory and relativity, in some sense, on the basic level, the situation of Newton's laws has survived. Because the Schrödinger equation, which is the basic equation of quantum mechanics, is again time reversible and again deterministic. we tried to see what happens further away. What happens when you are far from equilibrium? Not close to equilibrium, but far from equilibrium. And there, we had a great surprise. Because far from equilibrium, the situation changes completely. And it changes because far from equilibrium, at some point you may have new situations, new structures. And there, in a sense, you see the opposite of what I said about near equilibrium. We have the minimum entropy production. Far from equilibrium, you have more. It's not quantitative, but I'm saying it's a little qualitative, but still qualitative, it's true. You have the occurrence of new processes, new structures, which permit to cope with the non-equilibrium conditions. And that is especially clear in hydrodynamics and especially clear in chemistry. And we know now that these phenomena are of great importance in many fields, be it history of glaciation, ecology, or whatsoever. Now, let me give you an example of chemistry and an example of hydrodynamics. There is an example of hydrodynamics which was known since the beginning of the century, but not understood in this way, is the so-called Bénard instability, in which we heat a fluid layer from below, and then at some critical distance from equilibrium, that is, if we heat enough from below, then we see the appearance of vortices. Billions of molecules follow billions of molecules. Now, this is a highly non-trivial phenomenon. This could never be produced at equilibrium. The probability of it would be zero. And still, every time you introduce an arrow of time by heating, the system includes this structure. Now, chemical reactions. Well, what we have shown is that when the chemical reaction is nonlinear, has catalytic aspects. So you need a particle, a chemical compound to produce itself. For example, you produce X, which produce Y, which produce again X. Well, in such kind of situation, you expect that you cannot extrapolate from equilibrium. At some point, a new structure appears. And the structure may be a chemical oscillating reaction, or a space structure, what's called the Turing structure. And all this has been observed. And I remember always the amazement when we have seen really this in reality. First, the amazement when we have seen this on the computers. You see, because we had some simple models which are still around, the Bruxellator, on which we could verify this all on computer, in computer work. But then the